Hello, so this is a bit of a correction to the Lagrangian which we were doing that day. So I think I have made a mistake which I wanted to rectify. So what I wanted to discuss that day was we were considering this Lagrangian, right? I hope you can see this red marker. Is that we were considering a Lagrangian for a free particle in a Minkowski spacetime, and if you remember that this is our uh, space-time, let's say the space-time metric, the flat space-time metric, and this is how you get the Lagrangian, right? And then what we were doing is that since we have got the Lagrangian, we wrote down the Euler-Lagrange equation for t. So we were getting t double dot equals to 0, you integrate it twice and you were getting something like this. You similarly have had the Euler-Lagrange equation for x dot, and when you integrate it twice, you get this thing, right? And then we know that because the particle we were considering was a time-like particle, which is to say like particles with mass, let's say me and you. So this was the velocity normalization condition which we used. So t dot and x dot can be found from here and here. And then when you have one relation like this, and then with the relation of the velocity which is dx by dt, so you get a relation like c is equals to va. We plugged it back and we were getting the values of these constants a and c, right? So with these values we substituted over here, and this is what we were getting. And here is where I went wrong, because what I told you guys was that from this Lagrangian we would get the Lorentz transformation, but that is not the case. Actually, these equations, as we know, that is when you have a Lagrangian and you do the Euler-Lagrange equations, you just get the equations of motion. So this is just the equations of motions you will get. And now the idea is that maybe these could be utilized to find out something more when there are two frames involved. So now I go into this detail over here. That suppose you have one frame S and you have another frame S prime, and I say that both of them are related by some velocity transformation, right? So I don't know the form of gamma, right? So right now I'm not claiming that what the value of gamma is. Obviously you know this is the Lorentz factor and all and blah blah blah, but right now I'm saying that we do not know this, right? And now let's try to use the things we had found out, that t and x, substitute it over here and see whether we can infer what is the form of gamma, right? So just to repeat, you have a S frame, you have S prime frame which is moving with velocity v. You know that for a particle, because this is the case of a particle moving in a Minkowski space, right? It's just moving with some velocity over here. You know that t and x, the equations of motion are this. So you know that the prime frame and the unprimed frame are related by some transformations. The value of gamma you don't know. You substitute the value of x and t, so you substitute it over here, and you will get x prime equal to this, which has these d and b constants. So let those be here. Similarly, you substitute the value in t prime. So in t prime also you know what t and x is. This is what you had found out, and you substitute it like this, right? And now we also know one more thing. We know that the particle which is moving is again a time-like particle, right? Because we are discussing like normal electrons or you and me which are moving. So that's why that will have its own normalization condition. So we know that t dot prime square minus x dot prime square, this will be equals to 1. You know your t dot prime, you can find it out from here. So here when you will take t dot prime, you only this guy will left, this and this will vanish. When you will take x dot prime, this whole will vanish because there is no tau dependence over here. And here is what I think is interesting. What you are getting is you are getting something like, yeah, so you are getting t dot prime square is gamma square 1 minus v square, and minus 0 is equals to 1. We know that this equation is true, and you can just infer from here that this equation gamma square 1 minus v square, I am saying this is equals to 2. You don't know the form of gamma, so now you know what gamma is. Gamma is equals to 1 by under root 1 minus v square, right? So this is, I think, one of the ways you can find out the value of gamma. And one more thing is that because we have found this gamma and whatever and what, we can also find out that how the spacetime metric will remain invariant, because uvaga ds square is the guy which will remain the same for the guy who is over here and the guy who is over here. So if I calculate ds square as c dt prime square minus c dx prime square, it should be the same as c dt square minus dx square, right? Because there is some physical law which should remain invariant, and that is the space-time interval ds square. So this ds square, you can actually evaluate it like t prime t dot square minus x dot square, and this should be equal to t dot prime square minus, say, you substitute the values which you have initially get. So you substitute t dot from, I think, over here. So this is t dot. You can substitute it here. You will get just 1 minus 1 upon under root this square. You substitute x dot, which is from here. You substitute t dot prime, which is from here, and x dot, which obviously will be 0. So here what you are seeing is that you are getting an equation which is actually giving you, I'll just write it here again. So this is what you are getting. So if you will solve this, you are getting 1 minus v square minus 1 minus v square on the left hand side, and this is equals to gamma square minus 1 minus v square. And I'm claiming that this is equal, but why this is equal you can actually see, because this and this will just give me 1. The value of gamma you have already evaluated is 1 minus v square under root. So gamma square would be 1 minus v square. This is 1 minus v square. So this means that 1 equals to 1. So this guy is invariant. And why it is invariant? That's the important thing, is that there is a set of transformations between these two frames. So rest frame and moving frame, there is a set of transformation with this such and such that the gamma satisfies this value. And how do you get this gamma? You can get this gamma from the Lagrangian, as we got via this weird way, but I think this is how one can look into it. So just to reiterate, specify my point again, is that when you have the Lagrangian of a free particle, right, moving in a Minkowski space, you get the equations of motions, nothing fancy over here. But once you use these equations of motion in transformation laws between the two frames, and mind you, in the transformation laws where I don't know what the transformation law is, I do not know gamma, I know it's some function of velocity because this is moving with v. But when you substitute this, you find out that gamma is equals to 1 upon under root 1 minus v square. And what do we get from this? We get that because the particle is moving in the flat space time, if I calculate this ds square for this guy, the rest frame, or this guy, with the help of this gamma, I am seeing that they both are equal. So this is the one thing you can say, that this is how you prove that your space time is invariant between two frames with the given Lorentz transformations. And why Lorentz? Because this gamma is 1 upon under root of 1 minus v square, which you have actually derived. You do not assume it over here. So this is how you sort of get it. I hope this is correct. If wrong, then I will make another boring video.